Hi, my name is Christian Flügel from Pendar Technologies. I want to talk today about our high power quantum cascade laser solutions. Those are lasers in the mid-infrared spectral region, which can be used for spectroscopic applications. But here I want to specifically talk about their application in areas like infrared countermeasures. This is work we're doing for MWIR. We're towards the end of year two in our phase two effort. Before going into the technical details of our lasers and in the application space, I just want to quickly introduce our company, Pendar Technologies. We're kind of incorporated in 2010. We're located in Cambridge, Massachusetts, and have currently about 40 employees. Our team has a very successful track record of developing and also commercializing advanced laser technologies and spectroscopic instrumentations. Here at Pendar, we released about 2 years ago our first product. It's a handheld Raman spectrometer that you can see on the right side to detect for standoff detection of explosives and other nasty components. We're doing most of the prototyping, R&D, and manufacturing in-house. We have semiconductor fabrication capabilities, packaging capabilities. We're doing all the optomechanics and also electronics testing, algorithms, and so forth. So we're really mostly vertically integrated with certain aspects being outsourced, but overall we control the design and in the application of our systems. So the markets we are targeting is I think, broadly speaking, twofold. So one is the spectroscopy instrumentation market for safety and security, but also medical and other applications. And this one currently we serve with our Raman solutions, but we're also developing infrared spectroscopy solutions, which are based on our proprietary quantum cascade laser technology. But this quantum cascade laser technology can also be applied to high power applications such as infrared countermeasures. And this is basically what I want to focus on today in this presentation. Threats from heat-sinking missiles have long been a concern for all vehicles deployed on the battlefield. That includes aircrafts, but also surface ships and others. So that means all services really affected are in search for solutions to defeat those missiles. So there are currently solutions for this countermeasure application, and this includes solutions that already deploy quantum cascade lasers. But as the missiles and the tracking mechanisms are getting ever more sophisticated, we need to develop new solutions to defeat those more advanced threats. This will include increase of the output power, the spectral bandwidth, and also the operational flexibility. We're addressing this with our approach that I'll show in the following slides. But another aspect that's also very important is cost and reliability if those devices should be deployed in the field. And our solution not only addresses those performance requirements in advances, but we're also trying to make sure those devices are very reliable, and as volumes increase, can be developed and manufactured at a reasonable cost. Our solution that we present here, I think, is unique in that it addresses several aspects simultaneously. So one is it's a monolithic semiconductor laser solution. So it's a very compact way of scaling the output power. So beam combining means we can ensure that we still have excellent beam quality. And the surface emission scheme that I'll talk a little bit more on the following slides will also allow us to make those devices more reliable because we eliminate certain failure mechanisms that are very common in semiconductor lasers, which typically show up at the facets. So it will lead to improved reliability, but it's also a very straightforward way to make use of this surface emission geometry to increase yield, manufacturing yield, and with this reducing the cost of the devices. And basically all services that are in need of next generation IRCM solutions based on infrared lasers will benefit from such advances. So yeah, just to summarize again some of the key features of our solution. So our approach is based on quantum cascade laser array technology. Those monolithic arrays we've been developing for more than a decade. Initially, it started with making monolithic widely tunable single mode arrays for spectroscopic applications, and we have fully packaged and integrated prototypes with electronics, software, and beam combining, which you can see on the lower right side. But we can also use this platform for high power applications. So yeah, we have monolithic chips with several emitters on them, doing the proper thermal management and proper chip design. This can generate high power in the mid-infrared. This is a fully monolithic solution. It's a semiconductor chip, so there are no moving parts there, and also the beam combining is done with no moving parts. It uses external micro optics, which can be done in a very rugged manner. So specifically to this program, this MWIR program that we are presenting here today, is we're going one step further. So we want to move away from facet emission, which is usually used these days for basically all quantum cascade lasers. But those facets are known to be failure prone, especially in the presence of high thermal gradients and high optical power. So we are developing a surface emission geometry where the light is emitted through the substrate. And this has several advantages. So one is improved reliability, simplified integration into packaging, but also improvements in terms of reliability and cost. So what is the current status of our technology? So high power quantum cascade lasers with watt level output and high power QCL bars with multi-watt output have been developed, and I think this technology is established, although it needs to be matured beyond where we are right now, especially with respect to the arrays. But the risk is low, and for the bars, medium. As this is something that's been developed and shown. Key part to making reliable and well-functioning high-power QCL bars in arrays is to have very good thermal solutions, which we've developed and tested. And the same is true for high-power electronics, especially if you want to give the user improved or increased operational flexibility with kind of different operation schemes. We need to make sure we have custom electronics, which we also developed in-house and are routinely using for our arrays. So I think here the risk is very low. The same is true for beam combining, which we have established and developed for spectroscopic solutions, and the same concept is already being used for our high power arrays. The surface emission, we have shown proof of concept, so it does work. The fabrication is done with standard 3-5 semiconductor fabrication methods, so there is no strange or sophisticated fabrication needed. So it can be done in a high volume semiconductor fabrication environment. And we also showed good performance in beam quality. But this is under development. We've shown proof of concept, it works, but more work needs to be done to really implement this in multi-watt high power bars. So what are the key features and advantages and also benefits of our technology? So first of all, that's generally true for quantum cascade laser. It is a semiconductor laser. And it's based on 3-5 materials. So it's well established. There's a clear path to cost-effective scaling of production as the volumes increase. And this in turn will lead to a reduced cost and also being a semiconductor laser, low weight in power and size. The quantum cascade laser, the same material system can be used, that's indium phosphide, but it can be used for mid-wave infrared and long-wave infrared. So we use the same platform to cover the full kind of both atmospheric windows in the infrared. Again, this can lead to cost reduction and high flexibility in how we leverage this technology. The array configuration, obviously, it's a monolithic solution and it can, in a very straightforward way, lead to increased output power, especially if coupled with smart beam combining solutions. So you maintain high brightness, but you scale the power without putting too much demand on a single emitter. We're also using distributed feedback ratings to select specifically and very accurately select the wavelengths on each of those individual emitters. So we can really shape and control the emission very accurately, which is important for beam combining, but it also helps us to make sure and tailor the devices so they show most efficient performance for specific applications. For example, we can avoid atmospheric absorptions and other interferences for IRCM applications where you need to transmit the light over long distances. So all this is very well established and something we routinely do for spectroscopic solutions, but also for high power. Then surface emission, again, which is kind of the main focus of this particular program. We eliminate the need for failure-prone device end facets, which will lead to improved reliability and lifetime of the devices. It will improve and simplify the chip mounting because, again, we don't have to deal with facets that need to be accurately aligned with the end facets of the submounts and so forth. And what it also does is it will enable wafer level testing, burn-in solutions, and other things, and reduce or improve yield because you don't define the facets by using cleaving. So again, it's key to further reduce the cost for high volume production. So other market opportunities we're pursuing with our infrared or quantum cascade laser platforms are kind of spectroscopic markets such as explosive detections, gas analysis, and so forth. We are planning to introduce later this year a broadly tunable laser source for those markets. We're also developing QCL-based gas sensor full systems for either single or multiple gases. And in general, I think there's a lot of synergy between high power and those broadly tunable lower power devices that we use for spectroscopy. And any advances made in areas like manufacturing, output power, spectral control will benefit both of our platforms, whether it is spectroscopy or high power applications such as infrared countermeasures. So we are actively looking for transition opportunities of our high power QCL emitters and high power QCL arrays to further mature them. And we're looking into specifically phase 2.5s or equivalent Then in general, we're also looking for commercial partners and primes to integrate our solutions into full IRCM systems, and are also open, obviously, to explore other applications where those high power lasers could be used. As far as surface emission goes, we are looking for additional government support to further develop and mature the technology, but we're starting from a very solid starting point of having already demonstrated prototypes using mature manufacturing techniques that do show surface emission. And then for the broadly tunable single mode laser arrays that we use for sensing, there are also a lot of applications like threat detection in the safety and security and defense markets. And if you're interested in exploring using our arrays for those applications, please get in touch with us, and we would also be happy to discuss this with you in more detail. Thank you for listening to this talk about our next generation infrared laser solutions. If you want to discuss any of this more, we'd be happy to set up a phone call or a meeting with you. You can either contact me or my colleague, Dr. Laurent Deal, to set up such a meeting. And yeah, we'd be happy to explore opportunities for collaborations. Thank you.